In previous video, we solved heat equation with finite difference method. In this video, we will solve the same equation with finite volume method. I will not solve it completely. We will learn that technique in future. So what happened in finite volume method is first you generate a grid. For example, you generate a grid points, and then you take a middle of these two grid points like this, which I already have drawn over here. So this is called the um control volume like this. For example, this will be xi minus 1/2, since this node is xi and that node is xi plus 1. If I call it xi minus 1 and I call it this xi, and that one is xi plus 1, something like that. Okay, so these are the faces. This one is the xi plus 1/2. To generalize, we use such kind of structure in finite volume method where we have nodes. You draw an imaginary line which is called the face of the control volume, and so on. So what we do, we actually integrate this equation on this face. So we integrate xi minus 1/2 xi plus 1/2 partial u by partial t dx is equal to d, and we integrate the second derivative as well. Xi plus 1/2 partial square u by partial x square dx. Remember that on the right hand side we have one image which we will talk about later in this course. These are the nodes. These are the actual nodes, and this is the control volume. On the right hand side we have one node, and then we have a control volume. So you can see the difference. We will talk about that in future. This is called cell-centered finite volume, cell-centered finite volume or control volume, and this is called node-centered, since there is a node which is centered in this control volume. Node-centered finite volume. So in this case, in our case, we are using node-centered, cell-centered finite volume method. Mostly in finite volume method, we use cell-centered scheme. So this is actually in 2D. This is in 2D, two-dimensional, but in our case, we are just talking about in one-dimensional. So we integrate it. Remember that to construct a grid, you need a spacing, delta x, b minus a over n, as we did in finite difference method. And also we need the center of finite volume method. As you can see that these are the faces of control volume. So we need a formula which is xi I minus 0.5 delta x, and I will be from 1 to up to n. This formula is not for generation of the grid points. It is for the center of the grid points, like this. Okay. For example, if I put I is equal to 1, you get 1 minus 0.5, and delta x, for example, A is 0 and B is L. So this will be L minus 0 over N, and what we call it 0.5 L over N. If L is, for example, 1, then you get 0.5 by N. Whatever you choose, N is number of control volume that you want to consider in your calculation. Since I am just solving it without uh, taking particular values, so this is general problem. So what we do from here, we integrate this. On the left hand side, we have d by dt xi minus 1 half xi plus 1 half u dx, and on the right hand side becomes d partial u by partial x xi plus 1 half minus partial u by partial x xi minus 1 half. On the right hand side, you see that when there is one derivative, for example, if we have f dash x dx, calculus tells us that this derivative will be cancel out with integration and we get f of x. Okay, or in other words, when we have antiderivative, then it will be equal to this term. Okay, when we take the derivative of this right hand side f dash x, we get this term. Okay, so one derivative will be cancelled out since we have two derivatives. Let me explain it. Partial by partial x, partial u by partial x dx xi minus 1 half xi plus 1 half. So this integration and derivative will be cancelled out. We do not cancel it properly, but it is due to the Leibniz theorem or due to the calculus. So we get partial u by partial x, upper limit, apply upper limit, and then we apply the lower limit. Now the thing is, we have to find the derivative at xi plus 1 half and xi minus 1 half. So what is the strategy over here? The strategy will be to consider the values from the neighbors. As you can see, I draw it over here again. We have xi. This is xi plus 1 half. This is xi minus 1 half. You have to find the value of partial u by partial x at xi plus 1 half, and here you have to find the value of partial u by partial x xi minus 1 half. So what we do, we apply finite difference method. It will become partial u by partial x xi plus 1 half will be equal to u n nth level I plus 1 minus u n I divided by delta x. For example, we want to find the value of partial u by partial x at xi plus 1 half, and on the right hand side we have xi plus 1. We take advantage of neighboring values and apply forward difference method, and we introduce n in the superscript, which means that it is the solution is at nth level. Same goes to partial u by partial x, and we try to find it at xi minus 1 half, and you see that xi minus 1 half, we have one neighboring value at xi and another value is, for example, xi minus 1. In that case, we also apply forward difference. Since we go first forward, then we take value at I minus 1, and this is equal to delta x. After putting all these values over here, and I keep the left hand side as it is since I need to explain that a bit, d by dt, d by dt, xi minus 1 half, xi plus 1 half, u dx is equal to, right hand side becomes d un I plus 1 minus uni divided by delta x minus uni minus uni minus 1 divided by delta x. And what happened is we need to find, or we need to use some kind of values over here. The right hand side is now has been solved. This will be equal to d by delta x uni plus 1 minus 2 uni plus uni minus 1 divided by delta. Delta x has already been written over here. Now we invoke calculus again, and we know that if we need average value, the formula is, I think I have written somewhere over here. No? Okay. Yeah, over here. So this one is the average value and the definition of average value. So we do the same on the control volumes. In this control volume, we want to find the average. So the average will be equal to, by definition, it will be equal to d by dt delta x and delta x and xi minus 1 half. Average value will be equal to u hat or something, right? But since u hat will be the approximate value, and we want to keep same u on the left hand side and right hand side, this u hat will be equal to u. So this, the left hand side smartly will be equal to delta x u by using the definition. If you don't understand, I just try to make it simpler. Xi minus 1 half, xi plus 1 half, and we have u dx, and if we use the u hat average value or u average, 1 over delta x. You multiply delta x over here, this becomes u average, and xi minus 1 half, xi plus 1 half, u dx. That's what I did, and then I approximated u average with u. Now we have on the left hand side the derivative integration has been gone from here, and we solve it by applying Euler's method, un plus 1i uni plus d delta t. This dt will be multiplied on the right hand side divided by delta x squared. This delta x will be divided on the right from the right hand side, uni plus 1 minus 2 uni plus uni minus 1. So this is the equation for discretization equation to solve the heat equation, which is diffusion equation. And probably you remember that from the previous video, that we got the same equation from the finite difference method. Actually, the difference between the two method is due to the construction of this scheme. In this finite volume method, we integrate the differential equation, and in finite difference method, we directly apply the forward, backward, or central difference scheme. Okay. Thank you for watching.